What I would like to present today is a kind of curiosity-driven, rather early exploration research that we had. Just to give you a little bit of background, what we do at our university. So we are focusing, we do have a research network called ASPARI that is primarily focused on improving asphalt quality by looking at what's happening during the construction phase. And we argue that a lot has been done about roads and asphalts, of course, but the majority of the focus has been on condition assessment and material design. So we focus on the design phase and a lot also on condition assessment and rehabilitation, but we don't look at actually the contribution of the construction phase itself on the quality of the asphalt. And the entire argument of ASPARI is that there is actually quite a lot at stake during the construction phase, because asphalt is a very tricky material. You have only one shot to get it right. And if you don't perform the compaction properly, then the consequence of that mistake or error is usually extremely high, proportional to the actual cost of the project. So it's very important to look at this construction phase. And most of the time, what is being done right now is, although the quality of the asphalt is normally assessed in terms of whether or not you're meeting the density requirements, whether or not you're getting the actual thickness, the monitoring that is done during the construction phase, because of all sorts of limitation, is normally limited to do equipment move smoothly, do trucks come at the right time. So we are not really able to properly monitor what's happening with the material itself, mostly because of the technological limitations. So that's what we are trying to focus on. What can we do in order to better monitor and track the construction phase of the asphalt roads? And Netherlands is a rather specific case because since about 10 years ago, all the contractors in the Netherlands, they are bound to provide the guarantee of between 7 to 10 years for all the roads that they build. So that gives them a lot of incentive to actually improve. And within ASPARI, we created a network of the 10 major road constructor in the Netherlands. Collectively, they account for about 80% of road construction in the country. And we collaborate with all of them together in a network environment to look at this specific question of how to improve the construction phase. So, all right. So what's happening right now in terms of monitoring the construction phase? If you look at the literature and also our own past research, we've been focused a lot on indirect measurement of the quality. That's what I said. So we are looking at temperature homogeneity of the asphalt, whether or not when the paver lays the asphalt on the ground, is the temperature homogeneous? Does the compaction passes happen to the right number that is required? Is it consistent? Is it done at the right temperature? So these are the things that we can actually monitor, and we've been doing it quite successfully over the past years. But then the major question is, how do we know if the temperature is homogeneous and if the compaction has been done properly, that lead to a good quality asphalt, whether or not we will get density? That's the question we couldn't answer over the past few years. So while most of the work was done on really indirect measurement of asphalt quality with quite a bit of assumption, not much is done on the actual monitoring of the physical and mechanical properties of the asphalt and the propagation of those properties during the construction phase. So there are already some, tools that people can use. Like for very critical projects, they have this nuclear density gauge units that they can use, and they can do spot measurement during the construction phase. There are some GPR-based methods as well. But then because this kind of method would require a kind of specialist to be present on the site, this can't be scaled up. So that's a major problem for most of the contractors because they can only apply for highly critical roads and not actually all the roads. So we were just wondering, as I said, this was a kind of curiosity-driven project. Can we use computer vision to monitor the texture of the asphalt while it's being compacted, and then track the changes in the texture and see if we can just pick up some changes in the texture. And then later on to see or to investigate whether or not these changes in the texture of the asphalt could be correlated with some mechanical and physical properties of the asphalt and how they change, or better say with density and thickness. Can we relate the changes in the texture of the asphalt with the density propagation? So that was the main question that we asked, and we had no answer for that. So and based on our literature review, there was no precedent. So that's what I said. The entire research is kind of a curiosity-driven project. So in terms of texture analysis, there has been quite a bit of research before, but most of this research, what we realize is that they are done for condition assessment. So people have been using computer vision to detect cracks, to detect or to assess the skid resistance, raveling and bleeding detection. So these could be done, but these are mostly for operation phase or condition assessment of roads, and they cannot be actually applied for monitoring the or to track the density propagation of the asphalt. But of course, some of the core methods could be used for the purpose that we have at hand. So the main problem that we try to address is whether or not computer vision could be applied for monitoring asphalt pavement properties during the construction phase. And the objective was to actually do exploratory research into whether or not this is feasible and to what extent. So I'm going to skip this very simple design science methodology. So our vision ultimately, if this works, is to put two simple cameras in the front and back of rollers, and then they can monitor the texture of the asphalt before and after each compaction pass. And of course, all the rollers within Asparity are already equipped with GPS, so all the data is fully georeferenced. And then we would like to map the texture analysis that we do to a kind of predefined grid structure on the road. And again, that's something that we already do with the temperature monitoring and compaction pass analysis. We would like to only be able to now superimpose or map the imagery that we get from the camera to that existing cell structure, and then look at the texture within each cell over time. So a lot of compaction would happen. It could be done by multiple equipment, but then if they are properly georeferenced within a predefined grid, you could always track and trace what's happening before and after each compaction pass. So that's the overall vision that we have in mind. So we did a couple of experiments. I'm going to only present one of them. We did a lot more. And most of our experiments or case studies were on actual construction sites. So our student went to the site. Well, as I said, the ultimate vision is to put the camera on the equipment, but only for the feasibility analysis, it just made a lot more sense to use a stationary camera to remove all these issues with the vibration that comes from the camera, the steam that comes from the equipment. So those kind of things we would tackle later, but for now, we just wanted to see whether or not it's feasible. So we use this stationary camera, and then we move this, we created multiple stations across the road. We monitored a segment of the asphalt, and then we manually track when the compaction is done with the timekeeping. And then we use three different texture analysis methods: autoregressive models, the fast Fourier transformers, and basic segmentation method, which basically tries to only detect voids in the texture of the asphalt. And the other two, like the fast Fourier, would give you kind of a global analysis of that specific frame. And then autoregressive is more localized to different, let's say, pixel of the frame, but then it will take the overall average to give you some sense of consistency of what you would see in each frame. So for the basic segmentation method or void analysis, what we've seen in most of the frames that we actually looked at, you can easily see a trend. So the number of voids, and this could not necessarily, 2 minutes, 1 minute? No, all right, okay, so I will skip. So what you could see is that you can easily see a change in the pattern of the voids. The same happens with autoregressive model and fast Fourier method. So you can easily see, again, the number of roller passes, either consistency and or entropy of the frame, the frames that you will get from the cameras would change. And then there is quite a high correlation between this texture analysis and number of compaction passes. So about what we want to do in future, of course, the major challenge for us was to have some data about the density. So in the projects that we observed, we already coordinated with the contractors to bring a specialist with the nuclear density gauge, but that's something that that cannot be scaled up. So we already made arrangement with the contractors that we work to set up some kind of lab setting that allows us to use baby rollers or a slab compaction machine to be able to replicate what we want to do in a more controlled environment and hopefully get more data for the correlation analysis. So far, the conclusion is it seems very promising. There seems to be high correlation between the texture analysis that we get and also changes in the properties of the asphalt. So we definitely would like to follow up with this research. And as I said, the next step of the research is to collect more data in more controlled lab environment. Thank you very much.